All right, we have a given reaction and they would like us to determine each of the following: the order of each reactant in the reaction, the rate law expression, the overall order, and then the value of the rate constant, baby K, with the appropriate units. So my first thing is to write out the generic the generic rate law for this reaction. The generic rate law, also known as differential rate law or just rate expression. This is ultimately what we are solving for in part B. It is the word rate equal to lowercase k times the molarity of reactant number 1, mercury chloride, raised to some unknown power of m. That's called an order. That's what we're going to be solving for. Times the molarity of reactant number 2, raised oxalate with a charge, raised to some power of n. Again, that's the order of the oxalate ion. That is what we are solving for. So this is your generic expression. This is never going to be your answer for a rate law. The answer for rate laws, we have to substitute in the correct exponents, what we call orders, for each one of the reactants. Notice here in a rate law, only the reactants show up in the rate law, never the products. All right, in solving for the orders of these reactants, there's two major methods, table logic and then the math way. I'm first going to show you the table logic, which is really helpful to quickly determine the orders, especially on multiple choice type problems where you don't really have to show your work. This is more of a thinking way of determining, okay, changing one reactant, how does that affect the reaction rate? So in doing this, we're just going to focus on the first reactant, the mercury chloride. And we're going to solve for M, okay, its order. And in doing table logic, I want to pick two trials or experiments in which mercury chloride is changing, but the other reactant, the oxalate, is remaining constant. And so when I look at my data here, the two experiments that I want to focus on are experiment number 2 and experiment number 3. And that's because the oxalate is being held constant here. So I know that the change in rate is due only to the fact that we changed the concentration of the mercury chloride and nothing else has changed, assuming the other reactants are remaining constant and temperature is remaining constant. So I look and see how the concentration of mercury chloride has changed between experiment 2 and experiment number 3. For me, my brain works better when I increase in number, so I always try to think, okay, I go for the little number first, which is in experiment number 3, the concentration of the mercury chloride doubled essentially. So we did times 2. 0.04 times 2 gives me 0.08. And then I look and see how that times 2 has affected the rate of the reaction, which is in this last column here. And since the exponents here on the 10 are both -4, I can essentially ignore that times 10 part. And really what we're looking at is 1.06 changing into 2.08, which is roughly times 2. It's not always going to be perfectly times 2, but that is a very good estimate that is changing by a factor of 2. Okay, so since mercury chloride doubled, the rate doubled, and everything else is remaining constant in this reaction. When we change the reactant concentration and it causes the same exact change in the rate, or what we say is directly proportional, that order is going to be first order. All right, so what words would I have to write in order to get credit for this problem? This was free response and I had to show my thinking. We would have to say doubling the concentration of the mercury chloride caused the rate to double, while the concentration of the oxalate and temperature are held constant. This second statement is still important because we're assuming that temperature is remaining the same, so rate constant's being held constant, and then holding this oxalate concentration the same, we're pinpointing the fact that the rate change is strictly due to the change in the mercury chloride and nothing else changing. So we would say first order with respect to mercury chloride. All right, now we're going to solve for the oxalate ion, which means we're going to solve for that power of N from our generic rate law. So I'm going to do the same thing. I'm going to look for two experiments in which the oxalate is changing, but the other reactant, the mercury chloride, is being held constant. And so I'm going to focus in here on experiment number 1 and experiment number 2. And I see here from experiment 1 to experiment number 2, the concentration of oxalate is double times 2. And then I look at how the rate changes with that change in concentration. And I see here that it has been multiplied by 4. So 0.5 times 4 is roughly, is 2. So this is being increased by a factor of 4, what we can say is quadrupling. So since we doubled oxalate, but we quadrupled the rate, so that means the order of the oxalate has to be 2, because 2 squared is 4. So let's write this out in word format so I could get my credit for my thinking if I'm doing table logic. All right, to get my points and to show my thinking, we would say doubling the concentration of oxalate caused the rate to quadruple while the mercury chloride concentration temperature held constant. Therefore, it is second order with respect to the oxalate ion. So we have just determined the orders of each reactant. Now for part B, they would like for us to write the rate expression, also called the rate law or differential rate law. That is simply plugging in the exponents into the rate law. So you go to that generic equation that we've already written down on our papers. We're now going to substitute in the value for M and the value for N that we just determined. We said that the reaction was first order with respect to the mercury chloride, so it gets an exponent of 1. We said that it was second order with respect to the oxalate ion, so it gets an exponent of 2. What you have here now is no longer your generic rate expression. This is the answer for part B. This is what we call the rate expression, or also known as the rate law. Notice we have the word rate written out. That is equal to baby K times the molarity of reactant 1 raised to its power times the molarity of reactant 2 raised to its power, which we call orders, and those orders are determined using experimental data, never the coefficients from the balance equation. All right, now to solve the problem in the math way. We still write out that generic equation, no matter if we're choosing table logic or the mathy way. I'm still solving for the orders, which are the exponents, M and N, in our generic rate expression. And so our choosing of the experiments is the same as the table logic. It's just now we're just going to write out the math as our verification instead of the words as our explanation. And so in solving for the mercury chloride, I still want to pick 2 experiments in which mercury chloride is changing, but everything else, that other reactant, needs to be held constant. And so again, we're going to focus in on experiment number 2 and experiment number 3. All right, so for the math way, we're going to take the larger values, which was going to be experiment number 2, and divide that by the smaller values, experiment number 3. Essentially, what you're doing for each experiment is you're plugging in all of the conditions into the generic rate law for that experiment. So for experiment number 2, this is what you would plug in. All right, so I'm grabbing the rate information from the data table for experiment number 2. It has a rate of 2.08 times 10 to the negative 4 molar per minute because rate is change in concentration over change in time. And then insert baby K, and then the concentration for each one of our reactants. And we're just copying down the M and the N because we don't know what they are yet. And then we're going to divide all of this by experiment number 3, which I'm going to go to the data table and pull down the information. All right, so now we have our information for experiment 3. We'll see here a few things cancel out, and that's why we chose these 2 experiments. First of all, K's are always going to cancel out because they are the same in every single experiment. But here we see that the 0.404 to the power of n, they completely cancel out. This allows me to solve for m. Notice m is the only variable now in our equation, and we're going to simplify this and solve for m. 2.08 times 10 to the negative 4 over 1.06 times 10 to the negative 4. It's about 2. For our purposes, we can consider it to be 2. And then over here, 0.0836 divided by 0.0418 is going to be 2. All of that is raised to the power of m. So what does m have to be in order to have 2 raised to that power of m, and you get an answer of 2? M has to be 1. So this is first order with respect to the mercury chloride. So we'd write it out as, therefore, first order with respect to mercury chloride. Now we're going to go about solving for N, the order of the oxalate ion, in the same way. Examine your data table, pick 2 experiments in which the oxalate is changing, but the mercury chloride is not. Alrighty, looking back here at our data, I'm going to pick 2 experiments in which oxalate is changing, but the mercury chloride is not, and that's going to experiment 1 and experiment number 2. So we're going to do the same thing. I'm going to divide the larger values by the smaller values. So I'm going to take experiment 2 and divide it by experiment number 1. Alrighty, so we can see here a few things are going to cancel out. The K's are going to cancel out. The 0.0836 to the power of m is going to cancel out. And even since I already know what m is, and this is going to be helpful down the road when we get to some more complex problems, I could go ahead and substitute in the number 1 for our mercury chloride order, because we already solved for it, so you might as well just plug it in. But anyways, if you plug it in or you don't plug it in, it's going to cancel out because you have the same concentrations. All right, so now let's solve for N. All right, simplifying here, we get 4 is equal to 2 raised to the power of n. So therefore, n has to be 2 because 2 squared is 4. So therefore, this reaction is second order with respect to C2O4, 2 negative, the oxalate ion. Now for the rate law. We just did the mathy way. Now we need to answer part B. They want the rate law expression. So we go back to that generic equation and we substitute in our numerical values for M and N. So we're going to plug in M and N. M was 1, N was 2. So now this is your answer for part B. This is your rate law, also known as differential rate law or rate expression.